Okay, so here's a video for section 5.1, probability distributions and expected value. So let's jump right into it. First of all, let's talk about what is a probability distribution. A probability distribution is a table, formula, or graph that provides the probabilities of a discrete random variable using any of its possible values. So today we're going to focus on, you'll notice that underlined table, we're going to focus on showing the probability distribution of a discrete random variable using a table. So what we're going to look at, we're going to have some type of discrete variable, and we're going to look at all of the possible values that that variable could take on, and then show the probability of each of those specific values happening. So a reminder, discrete random variable, a variable that has unique value for each outcome. So for example, the first one we're going to look at is rolling a die. So if you roll a die, that's a discrete, the number that shows up on the die is a discrete random variable. And what possible values could show up when you roll a die? Well, you could roll a 1, or a 2, or a 3, or a 4, or a 5, or a 6. Okay, those are discrete values. If we wanted to show the probability distribution for the value showing up on a die, we would also then need to figure out the probability of each of those values occurring. And, we'd have 1 over 6, 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 1 over 6. Okay, this is a very just rough table, not very organized. But anyways, this would be a probability distribution shown as a table for the possible outcomes when you roll a die. Some properties of that table, you would notice the probability of each value of the discrete random variable is between 0 and 1, which means each possible value the variable could take on, the probability of that value occurring has to be between 0% and 100%. And logically that makes sense, and that's what this means here. The probability of each value x occurring has to be between 0 and 1, greater than or equal to 0, less than or equal to 1, and the sum of all the probabilities has to add to 1. So basically that means all of the probabilities added together have to equal 100%. Because if we've accounted for each possible outcome that could happen for a discrete random variable, if we add all of the probabilities of each of those together, it has to add to 100%. If it doesn't add to 100%, then if it adds to less than 100%, then you've clearly missed one of the possible outcomes that could happen for that discrete random variable. Or if it adds to more, maybe you've calculated a probability wrong or something. So make sure your probabilities add to 1, which means 100%. If we look back at this rough table I made here, you'll see the probabilities are 1 over 6, 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 1 over 6. If we add those together, we get 6 over 6, which equals 1. Okay, let's look at a more organized example here. So let's consider an experiment where we roll 2 6-sided die. And for this example, we'll have a red die, and we'll also have a blue die. So we're going to roll them both. And what we're going to do, we're going to consider an experiment where we want to look at the possible sums of the two die when we roll them. So our discrete random variable for this experiment is the sum of the two die. So in order to make this probability distribution, first of all, we have to figure out what are the possible values for the sum of the two die when we roll them. Well, you might think, okay, the lowest possible sum we could have is 2, because that would occur if I got a 1 and a 1. So that's the lowest possible sum I could have. And the highest possible sum you could have is a 12, if you rolled a 6 and a 6. And we could have anything in between there. We could get a 2, a 3, a 4, 5, 6, 7, 8, 9, 10, 11, or 12. Okay, so any of those outcomes are possible. So those are all the values for this discrete random variable of the sum of the two die. So if I want to make my probability distribution, in my left-hand column, for the values of x that may occur, that would be the possible sums I could have. I could get a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. Now, to do my probability distribution, I then need to figure out the probability of each of those values occurring when I roll the two die. So whenever you're calculating a probability, if I want to figure out the probability of a 2, I can figure out, okay, well, how many ways could I roll a 2? And then divide that by the total number of possible outcomes when I roll 2 die. So, and if I want the probability of rolling a 3, how many ways could I roll a 3 and divide that by the total number of possible outcomes? And same thing, a 4, 5, or 6. You're always going to be dividing by the total number of possible outcomes. So how many outcomes do I have when I roll 2 die? Well, there are 6 outcomes for the first die, 6 outcomes for the second die. So you'll notice our table of outcomes is 6 by 6. 6 times 6 equals 36. If you want to figure out the total number of outcomes for an experiment, multiply the number of outcomes in each step of the experiment, and that'll tell you the total number of outcomes. 6 outcomes for the first die, 6 outcomes for the second die, 6 times 6, there are 36 total outcomes. Okay, what's the probability that I roll a 2? Well, how many ways could you roll a 2? There's only one way. I only see 1, 2 in my outcome table. It's if I roll a 1 and a 1. So the probability of rolling a 2 is 1 out of 36, because 1 out of my 36 total outcomes are the sum of a 2. How many ways, or what's the probability of rolling a 3? Well, how many outcomes of the 36 are a 3? I see 2 of them. 1, 2. Why are there 2? Because you could roll a 2 and a 1, or a 1 and a 2. There are 2 ways you could roll a 3. You could roll a sum of a 3. So 2 out of 36 will give you the probability of rolling a sum of 3. How many ways could you roll a 4? Well, in your outcome table, you see 1, 2, 3 ways you could roll a 4, so 3 out of 36. You could roll a 3 and a 1, or a 1 and a 3, or a 2 and a 2. How about a 5? Well, you could look at your outcome table, and you would see that there are 4 outcomes that have a sum of 5. So 4 out of 36. You could roll a 4 and a 1, 1 or a 4, 3 and a 2, or 2 and a 3. And then for 6, and so on, you could keep going back, looking at your outcome table, figuring out all the possible outcomes, dividing it by the total number of possible outcomes, and this would be our completed probability distribution for the possible sums when you roll 2 die. And if you wanted to check and make sure you've done it properly, add them all together, make sure it equals 1. So they all have a common denominator, which makes it nice and easy to add them. So there's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 equals 36 over 36, which equals 1. If we wanted to display that probability distribution, so this is the probability distribution as a table. If I wanted to display it as a graph, on the y-axis, normally when we looked at bar graphs and histograms before, we had a frequency on the y-axis. Now we actually put the probability on the y-axis. So if I wanted to figure out and on the x-axis, sorry, we have the values for the discrete random variable. In this case, it's the sum of the 2 die. So we have the sum on the x-axis, so it could be a 2, a 3, 4, all the way to 12. For example, if we look at the 4 bar here, notice that the bar goes slightly above 0.08. And if we were to calculate the probability of getting a sum of 4, 3 over 36, let's see, we should get just above 0.08. So 3 divided by 36, we get 0.083. That's why the height of the bar goes just above the probability of 0.083. So the height of the bar now corresponds to the probability of the event occurring, not the frequency anymore. It's all about probability now. Notice this probability distribution forms a nice mound-shaped distribution. And if we were to add all the probabilities together using the graph, they should add to 1 as well. Okay. Next, the only other thing you're going to need to know how to do for this lesson is to calculate the expected value of a discrete random variable. So when you roll 2 die, the sums that could show up could be anything between 2 and 12, but if you were to do it once, what would you expect the value to be? So this formula looks fairly complicated, but basically all it is saying is the expected value of a discrete random variable, x, is the sum of the terms of the form x times px. So we're just going to focus on that. If we want the expected value of a discrete random variable x, we just need to do the sum of each of the values x could take on times the probability associated with each of those values. The sum of x times the probability of x. So let's see what that looks like. If I want to figure out the expected sum when I roll 2 die, I just have to do the product of each possible sum. So times its associated probability. So I would do 2 times 1 over 36 plus 3 times 2 over 36 plus 4 times 3 over 36. So do the product of each possible sum with its probability and then add them all together. So this is what it would look like. Expected sum, I could get a sum of 2, multiply that by the probability, you get a 2, plus 3 times the probability of 3, plus 4 times the probability of 4, all the way up to plus 12 times the probability of 12. So if I plug in all of my probabilities, the products of my probabilities with the values that they could take on, this is what I would get. 2 times 1 over 36, plus 3 times 2 over 36, plus 4 times 3 over 36. Why are these two paired together? Well, because I could get a sum of 4, and the probability of that happening is 3 over 36. If you look back at your table, 4 times 3 over 36. And then next would be 5 times 4 over 36. We look back, plus 5 times 4 over 36. Okay, so let's go ahead and calculate this so we can get our expected value. So notice they all have a common denominator. So that's going to be nice, make the calculation fairly simple. So I just need to do 2 times 1 is 2, plus 3 times 2 is 6, plus 4 times 3 is 12, plus 5 times 4 is 20, plus 6 times 5 is 30, 7 times 6 is 42, 8 times 5 is 40, plus 9 times 4 is 36, plus 10 times 3 is 30, plus 11 times 2 is 22. I'm just going to move all of this over slightly, so oops. Oh, this is being a little laggy for me. Okay, try this again. I'm just going to move all of this over so I can fit my last product in. And it's being very laggy. Okay. I don't know why. Okay, and my last product, 12 times 1, is 12. And then remember, all of these were over 36. So if I find the sum of my numerator, I'll get 252 over 36, and that equals 7. So when I roll 2 die, the sum I would expect to see would be a 7. Okay, let's do another example. This one may get slightly more confusing, but that's okay. I just realized I need to, so don't look too much right now. I just want to copy this to the other slide. So I'll read this while I'm doing this. So suppose you were to toss 3 coins. When we toss 3 coins, each time you toss a coin, right, there's 2 outcomes. You could get heads or tails for each time you toss a coin. We're going to create a table that shows the theoretical probability distribution for this experiment. The discrete random variable x, remember we call the discrete random variable x, represents the number of heads that we observe when we toss 3 coins. So if you toss 3 coins, we want to create a probability distribution for how many of those tosses resulted in heads. So if we think about it, when we toss 3 coins, what could happen? How many heads could happen? Well, we could toss 3 coins and all of them could be tails, meaning that we had 0 heads. We could toss 3 coins and one of them could be heads, the other 2 could be tails, so we could have 1 heads. Or 2 of them could be heads, or all 3 could be heads. These are all of the possible outcomes for the number of heads that could occur when we toss 3 coins. So, if I want to figure out, now, okay, to complete my probability distribution, I now need to figure out what is the probability of each of these values occurring for the number of heads. So if I want to figure out, okay, what's the probability of getting 0 heads? That would mean I would have to get, when I flip the 3 coins, I would have to get tails, and then tails, and then tails. And notice when I said that, I said tails, so I'd have to get tails, I'll just use T actually. I would have to get tails, and then tails, and then tails. When you say and, that means you need to multiply the probabilities together. So tails times tails times tails. So what's the probability when you flip a coin, you get tails? And oh, sorry, I should be doing this in red because I said up here I'll use red for tails. So what's the probability that you flip tails when you flip a coin? Well, there are two outcomes when you flip a coin, heads or tails. The number of ways we can get tails is 1, so 1 out of 2. You have a 1 out of 2 chance when you flip a coin of getting tails. So what I have to do, 1 out of 2, times the probability the second coin is tails is also 1 out of 2, times the probability the third coin is tails is also 1 out of 2. So for me to get 0 of, actually I'll change these to blue so you understand that our discrete random variable is the number of heads that occur. You don't get confused and think I'm talking about tails there. If the computer will stop lagging. Come on. Okay. Okay, so the probability that I have 0 heads when I flip 3 coins, that would mean I would have to get tails, and then tails, and then tails. So do the probability of tails times probability of tails times probability of tails. And that would give you 1 over 2 times 1 over 2 times 1 over 2. That'll give you 1 over 8. Okay, now I want to find the probability that one of my flips is heads. So that would mean I need to have one of my coins be heads. So what's the probability the first coin I flip is heads? It's 1 out of 2. Notice I used blue for this one because this one is going to be flipping a heads. Next, so if I need to, one of my 3 needs to be heads, that means, so if my first one is heads, that means my next 2 have to be tails. So I need to do heads, and then tails, and then tails. So probability of heads times probability of tails times probability of tails. So probability of tails for my second coin is 1 over 2. Probability of tails for my third coin is 1 over 2. Now, think to yourself, is this the only way this could happen? Is the only way I could get one of them heads would be getting the first one heads and then the next 2 tails? And if you think about that carefully, the answer would be no. If we want to figure out how many ways could one of my 3 outcomes be heads, well, I could start off by getting tails. I won't rearrange this too much because it'll take too long with the lag. But I could rearrange it like this. I could get tails and then heads and then tails. Or I could get tails and then heads. So basically what I'm doing, I'm figuring out how many ways could I choose one of these 3 spots to be heads. Another way to think of that is 3, choose 1. You might see it written like this, 3, choose 1. So we're going to use combinations. You need to remember that from the last chapter, section 4.7. This means how many ways can I choose? So I've got 3 outcomes here when I flip the 3 coins. How many ways can I choose one of those 3 spots to be heads? Remember, heads we use the blue for. So if we do 3, choose 1, you end up getting a value of 3. So that means there are 3 ways that one of the 3 outcomes could be heads. It could be tails, tails, heads, heads, tails, tails, or heads, or tails, heads, tails. Sorry, tails, tails, heads, heads, tails, tails, or tails, heads, tails. 3 ways, 3 choose 1. So I need to multiply this by 3 choose 1 because there are 3 ways that I could choose one of these spots to have an outcome of heads. That's what, so I'll draw an arrow from here, that's what this explanation is saying. Number of arrangements with one of them being heads. How many ways of my 3 spots could I choose one of them to be heads? And 3 choose 1 has a value of 3, so essentially I'm multiplying this by 3 because there are 3 ways that one of the 3 spots could be heads. So 1 over 2 times 1 over 2 times 1 over 2 times 3 is now 3 over 8. Next, if I'm going to have 2 of my outcomes be heads, I could get heads and then heads, and that would mean my third one would then have to be tails. Is that the only way that 2 of them could be heads? I could have heads, then tails. And you think, no, that's not the only way it could happen. I could have tails then heads, or heads then tails then heads. Once again, there's three ways. How you could calculate that if you want to. You could think of it as, okay, I know two of my three spots have to be heads. How many ways out of my three spots could I choose two of them to be heads? So multiply by 3, choose 2. 3 choose 2 has a value of 3. And once again, if you don't remember that, on your calculator you could just type 3 math probability NCR 2. 3 choose 2 has a value of 3. That means there are 3 different ways we could choose two of the spots to be heads. And you might say, well, hey, why don't I just do 3 choose 1 again and see how many ways could I choose one of the spots to be tails? And that's fine as well. You could think of it that way. You could do 3 choose 1 and you get the same answer. 3 choose 1 is the same value as 3 choose 2. So what we get here, once again, 1 over 2 times 1 over 2 times 1 over 2 times, remember this has a value of 3, we once again get 3 over 8. And why do we have 3 choose 2? Because that tells us the number of arrangements, 3 outcomes where 2 of them are heads. And now what if we flip 3 coins? Don't forget the last possible outcome, all 3 of them could be heads. So we could get heads times heads times heads. So 1 over 2 times 1 over 2 times 1 over 2. And that's the only way that could happen. I can't rearrange those any other way. So that equals 1 over 8. And if we look at all of our possible, all of our probabilities, 1 plus 3 plus 3 plus 1 is 8, so we have 8 over 8, which equals 1. So we've done our probability distribution correctly. So here's it written maybe a little neater for you. And now let's use our probability distribution to answer some probability questions. Once you have your probability distribution done, it's nice and easy to answer these types of questions. Like, what is the likelihood you would observe at least 2 heads? So if we think back to the values of our discrete random variable, we could have 0, 1, 2, or 3 heads. So if we want at least 2, that means 2 or 3. And when you think or, you need to think of the operation plus. So if I want 2 or 3, that means greater than or equal to 2 of them being heads, so probability of 2 plus probability of 3. If we look back to our probability distribution, probability of 2 is 3 over 8, probability of 3 is 1 over 8. Add them together, we get 4 over 8, which is a half, so a value of 0.5. Okay, what is the expected number of heads? So remember, we're going to use the formula for this. We want the expected value of our discrete random variable, and that means the expected number of heads. We need to figure out, we need to do the sum of each value the discrete random variable could take on, multiplied by the product of each of those, or multiplied, by the probability of each of those values occurring. So if we look back to our table, we just need to do the sum of x times px. So the sum of the value of the discrete random variable times the probability of that value occurring. So 0 times 1 over 8 plus 1 times 3 over 8 plus 2 times 3 over 8 plus 3 times 1 over 8. And this is what we would get. We would have 1 times 3 over 8. I'll just delete this, so you can see it better. So we have 0 times 1 over 8, which is 0, so that's gone. 1 times 3 over 8 is 3 over 8, plus 2 times 3 over 8 is 6 over 8. So we plus 3 times 1 over 8 is 3 over 8. So we have 3 plus 6 plus 3 gives us 12 over 8, 3 over 2, which is 1.5. We would expect 1.5 heads when we flip 3 coins. Okay, I'm going to do 2 more examples. I'm going to go through these ones a little quicker. Okay. So suppose you want to select a committee consisting of 3 people. So first off the bat, you might think to yourself, okay, I recognize these types of questions from our combination section last chapter, where we're forming committee from groups of people. And we are going to need to remember how to use combinations once again for this question. So we want to select a committee that has 3 people on it. The group from which the committee members can be selected consists of 4 men, so we'll do the men calculations in red, and 3 women to choose from, and the women will be in blue. Create a table that shows the theoretical probability distribution where the discrete random variable x represents the number of women on the committee. So before starting the table, how many possible committees are there? The reason why we're going to do this, because if you think about it, okay, our probability distribution X represents the number of women selected. So we need to figure out what values could X take on. If our committee has 3 people, well, on the committee we could have 0, 1, 2, or 3 women on it. Okay, if the committee has 3 people, none of them could be women, or 1, or 2, or 3 could be women. Those are the values X could take on. Then if we want the probability of each of those values, if I want to figure out the probability of 0 women being on the committee, I'd have to figure out, okay, well, how many ways could that happen? And then I have to divide that by the total number of committees that are possible. If I want the probability of 1 woman on the committee, I have to figure out how many ways could that happen, and divide that by the total number of committees possible. So that's why at the beginning here, I'm first going to start off with figuring out what am I going to be dividing each of the probabilities by. I'm going to figure out how many possible committees are there. So keep in mind there's 4 men and 3 women, so there are 7 people in total. And I need to make a committee of 3. So if I do 7 choose 3, that will tell me how many possible groups of 3 I can make from the 7 people in total. So that's why I'll do 7 choose 3, and it gives me 35. And once again, the shortcut on your calculator, 7 math choose 3, give you 35. Also, maybe I'll show you quickly just using the formula. If you want to do a combination, you can use the combination formula. Keep in mind this is your n, this is your r. You do n factorial over n minus r factorial times r factorial. And that will give you 7 factorial over 4 factorial times 3 factorial. Give you 7 times 6 times 5 over 3 factorial. Keep in mind this would be times 4 factorial, and then cancel out with the 4 factorial on the bottom. 3 factorial is equal to 6, so I can cancel those out. So I just have 7 times 5, 35. Okay, or you can just use the shortcut button on your calculator. So there are 35 total different groups of 3 I could make from the 7 people that I had to choose from. And also keep in mind I'm using combinations because we're assuming the order of the people in the group does not matter. Okay, and when the order doesn't matter, we use combinations. Okay, so number of women on the committee. We've established, okay, so since we're going to do blue for women, I'll use blue over here. Number of women on the committee. There could be no women on the committee. There could be 1, there could be 2, or there could be 3 women on the committee. Those are all the different possible values that X could take on if X represents the number of women on the committee. Now, keep in mind there were 3 women. I think there were 3. Yep, and there were 4 men. There were 4 men. So, if I want to figure out the probability of there being 0 women, that means, and keep in mind I'm making committees of 3, that means I would have to choose all 3 members of my committee from the group of men. Well, how many ways could I choose 3 men from a group of 4? Do 4 choose 3. And if you want, so we're going to need to have 3 men and 0 women on this committee. And we say and, you multiply. So I could multiply this by how many ways could I choose 0 women from 3. 3 choose 0. Anything choose 0 is just going to give you a value of 1. Because keep in mind, well, I won't get into it too much, but 0 factorial equals 1, and you'll have to remember that. But anyways, anything choose 0 is equal to 1. There's one way we could choose no women from a group of 3 women. So you don't even have to multiply by this 3 choose 0, but you can if it helps you. So if we're making a committee that has no women, that means we're going to choose 3 of the 4 men and 0 of the 3 women. Notice I said and, 3 men and 0 women. That's why we're multiplying these together. And don't forget we're finding the probability, so we have to divide this by the total number of possible committees that could be made. And we established earlier there are 35 total committees that can be made. 7 choose 3. 4 choose 3 equals 4. 3 choose 0 equals 1, so 4 times 1 equals 4. So our probability here is 4 out of 35. How about if on my committee I'm going to have 1 woman? If on the committee of 3 there's 1 woman, that means there are 2 men, so I'm going to choose 2 of the 4 men and 1 of the 3 women. So multiply by 3 choose 1. I'm going to choose 1 of the 3 women. And don't forget to divide this by the total number of possible committees that could be made. There are 35 committees that could be made. Okay, so now you're going to do 4 choose 2. If you do 4 choose 2, you'll get a value of 6, and you can use your calculator to do that if you want to. 3 choose 1 is 3. 6 times 3 is 18, so we have 18 over 35. I'll just show you quickly. 4 choose 2. 4 math choose 2 gives you 6. 3 choose 1 gives you 3. So 6 times 3, 18. 18 over 35, so probably the committee will have 1 woman on it. And what is this? Keep in mind, what does this 4 choose 2 means? That means how many different groups of 2 could I make from the 4 men if the order doesn't matter? And what does this 3 choose 1 mean? That means how many ways could I choose 1 person from a group of 3 women? And obviously there's 3 different ways you can pick 1 from 3. Okay, what if we're going to have 2 women on the committee? That means there must only be 1 man. So how many ways could I choose 1 of the 4 men? Times how many ways could I choose 2 of the 3 women? And divide that by the total number of possible committees. So 4 choose 1 is 4, 3 choose 2 is 3, so I have 12 over 35. So equals 12 over 35. Now, if on my committee I'm going to have 3 women, that means I'm going to have 0 men. So 4 choose 0. You don't need to include that one because that just has a value of 1, but you can if you want. And I'm going to choose all 3 of the women. And I'm going to divide that by the total number of possible committees. And I'm going to get 4 choose 0 is 1, 3 choose 3 is 1. I have 1 over 35. So there's my completed probability distribution for the number of women that could be on a committee of 3. 4 plus 8, 22, plus 12, 34, plus 1, 35. The sum is 35 by 35, which equals 1, which means we've done our probability distribution correctly here. Here's the probability distribution, maybe written a little bit neater for you. Now let's calculate some probabilities using our probability distribution. What's the probability that at least 1 woman is on the committee? At least 1. There's a couple ways we could do this. At least 1 means either 1 or greater. So 1 or 2 or 3. Because the committee consists of 3 people, so the most women that could be on is 3. So I could have probability of 1 plus probability of 2 plus probability of 3. Because remember we said or when we thought about this. To have at least 1, that means we could have 1 or 2 or 3. When you say or, you add. So if we go back, probability of 1 plus 2 plus 3, 18 plus 12 plus 1, that'll give us 31 out of 35. Another way to think about this, if we're going to have at least 1 woman, we could just think, well, how many ways could you have less than 1 woman, then subtract that from 100%. If you're going to have at least 1 woman, okay, that means the only thing that couldn't happen is this right here. This is the only thing that couldn't happen. We couldn't have 0 women if we're going to have at least 1, so subtract that from 1, or 100%. So 1 minus 4 over 35, that means 35 over 35 minus 4 over 35, which will give us the same answer. Probably greater than or equal to 1. We'll just do 1 minus the probability of not satisfying this, and the only way we can not satisfy it is having 0 women. So 1 minus 4 over 35 equals 31 over 35. What's the expected number of women on the committee? Once again, don't forget we'll use our formula, the expected number of women, so I'll use x for the number of women, equals the sum of each value of x times its probability. So if you go back to your table, you're getting 0 times 4 over 35, plus 1 times 18 over 35, plus 2 times 12 over 35, plus 3 times 1 over 35. And I'll just put up the answer quickly. I'm not going to go through it. If you find all the products, add them together, you get 1.3. So you'd expect 1.3 women to be on the committee of 3 people. Last example. I'm going to go through this one even quicker. Suppose you're dealt a 3-card hand from a standard deck of cards. Standard deck of cards, keep in mind there are 52 cards in a standard deck. Create a table that shows the theoretical probability distribution for how many spades are in your hand. So how many spades you have, that's our discrete random variable x. Whenever we want to figure out the probability of a certain number of spades in our hand, we're always going to need to figure out, okay, how many ways can we have that specific number of spades, and then divide that by the total number of hands we could have. So, before we can find any of the probabilities, we're going to have to know how many hands are there. How many different 3-card hands could you make from a deck of 52 cards? Keeping in mind the order of the cards in your hand doesn't matter, so we would just do 52, choose 3, and we'd figure out there are 22,103 different 3-card hands you could have. So when we're doing our probabilities, we're going to be dividing by 22,100 each time. So, I'm not going to color code this one. Hopefully we can figure this one out without color coding it. If our discrete random variable is the number of spades in our hand, keep in mind there are 13 spades in a deck. 13 spades, and there are 52 cards in total, so that means there are 39 non-spades. It's important to distinguish these two different groups here. 13 spades, 39 non-spades. So if I'm going to have 0 spades in my hand, and keep in mind I'm making a hand of 3, I'm going to have to choose all 3 of my cards from this non-spade group. So how many ways could I choose 3 cards from the 39? How many different groups of 3 could I make? 39, choose 3. And I'm going to choose 0 spades, so I'm going to choose 0 of the 13 spades. Divide that by the total number of possible groups, 22,100. So that's how we do the probability of 0 spades. So I want to do the probability of 1 spade. I have to choose 1 of the 13, then only 2 of the 39, and so on. And keep in mind, these are all the possible outcomes to the number of spades in my hand. If I have a hand of 3 cards, none of them could be spades, or 1, or 2, or 3. And here's a completed probability distribution for that. If I want probability of 2 of them being spades, I would choose 2 of the 13 spades, and, so multiply by 1 of the 39 non-spades. If all 3 of them are going to be spades, that means 3 spades and 0 non-spades. So probability of 3 spades, or the number of ways I could choose 3 spades, times the number of ways I could choose 0 non-spades. 13 choose 3 times 39 choose 0. These are all the probabilities. I'm not going to go through all the calculations. Hopefully you understand where all these numbers came from. Notice each time I'm dividing by 52 choose 3, the 22,100, because that's the total number of possible 3-card hands you could have. If you want the expected number of spades, just do each value of x times its probability, add all those products together, and you would expect to have 0.75 spades in your hand. So you expect to have less than 1 spade in your hand. And that's it. Let me know if you have any questions. Go to jensenmath.ca, download the worksheet, and try out some practice problems.